The morning of March 23, 2009 was a relatively quiet one at Narita International Airport outside Tokyo. The time was just before 7 o'clock and the horizon still had that pale, washed-out color of a spring dawn. From the control tower, the field looked normal enough. The runway lights were still glowing, and in the air above Japan, both passenger and cargo jets were lining up for their morning arrivals into what was then Tokyo's main airport. FedEx Flight 80 was one of those flights who was now nearing the end of its overnight journey, and for the two crew on board, this flight had so far been completely unremarkable. As the aircraft descended down, light to moderate turbulence continuously rocked the aircraft, but not outside their experience and capabilities. Now, what was about to happen to this flight would take only a few seconds, but leave the aviation world stunned. And in the aftermath, investigators would find a story that was much bigger than just one flight. This is a story about design compromises, training gaps, possibly a bit of fatigue, and a plane with a quirk that had already caused an accident to this exact airline more than a decade earlier. FedEx Flight 80 started off as a routine operation over from Guangzhou, China, towards Narita, Japan, just north of Tokyo. In the cockpit were two pilots, both with long and successful resumes. In the left seat sat a 54-year-old FedEx veteran captain whose career had begun in the US Marine Corps, where he had spent years flying Marine fighter aircraft before moving into commercial cargo. By the time of this flight, he had accumulated more than 8,000 total hours, of which over 3,600 were flown on the MD11. He was known among his colleagues as a nice guy who was steady, methodical, and someone that could be counted on to fly the aircraft by the book. Years of experience had given him not just technical skills, but also the kind of quiet confidence that comes from doing countless approaches in challenging conditions, including landings on ships at sea in all types of weather conditions. Beside him, he had a 49-year-old experienced first officer. Like the captain, he had come from a military background, having flown the absolutely massive C-5 cargo jets for the US Air Force. After leaving the service, the first officer had then transitioned onto commercial flying, eventually joining FedEx. And at the time of this flight, he had logged over 5,000 hours, but only about 879 of those on the MD11. So compared to the captain, he was still relatively new on the type. Now, I usually consider someone experienced on type at around the 1,500 hour mark, so with 879 hours, this first officer certainly wasn't a rookie, but he wasn't fully experienced with the MD11 either. And it's important to remember that cargo operations with long-haul aircraft often means long hours without necessarily doing many landings or takeoffs. But given this first officer's previous military cargo experience, which meant that he was used to demanding landings and the discipline of flying complex machines at night, the first officer would be operating as pilot flying on this flight, with the captain as pilot monitoring. And that was even though the weather on arrival looked like it could be quite challenging. The airplane that they had been assigned to for this flight actually had a quite complex and interesting history. It was registered as November 526 Fox Echo, and it had rolled off McDonnell Douglas production line back in 1994 as a passenger MD11, before then being converted into a freighter around a decade later. In between, it had also spent time as NASA's testbed for an experimental system designed to control an aircraft purely through engine thrust in case of a total flight control failure. Something that my colleague Ben actually covered over on Mentour Now, which you should really check out after this video. Anyway, by the time FedEx had acquired it, the jet was a well-worn but capable machine. One of dozens of MD11 freighters that formed the backbone of the company's global fleet. But the MD11 itself was always a point of debate among pilots. Born in the late 1980s as a stretched, modernized successor to the DC-10, it promised to launch McDonnell Douglas into new levels of success and allowed them to compete with the likes of Boeing and Airbus. The MD11 had computerized a lot of the functions of the DC-10, allowing it to move from a 3-person flight crew to 2, whilst also promising longer range and higher efficiency than its predecessor. But to achieve those numbers, McDonnell Douglas had also made some compromises. The engineers had fitted bigger, more powerful engines, which gave the MD11 plenty of power, endearing it to its pilots, but they had also reduced the size of the tailplane to cut down on drag, and also added some slotted surfaces, among other things. The result of all of this was an airplane that could fly further and faster than its parent, but at the cost of becoming a little bit more twitchy and somewhat hard to handle, especially during difficult approaches. Now, a lot of people have attributed these handling issues to that smaller stabilizer that I just mentioned, but in reality it had more to do with how the weight was distributed behind and in front the center of gravity, which gave the aircraft a bit of a barbell effect, making it a bit harder to get a pitch movement going. And once that pitch was going, it also made it harder to stop, which is worth remembering. Anyway, pilots who flew it quickly learned to respect these quirks, meaning that most landings were uneventful. But if you got behind the airplane near the ground, things could go wrong very fast. And at the time of this story, there had already been several landing mishaps with the MD11 fleet, specifically due to large bounces. Now, this crew, of course, knew this. Both pilots had gone through bounce recovery training in the simulator years earlier, so they knew the drill. Don't force the nose down, don't overcorrect, just hold the nose at around 7.5 degrees, and if things get unstable, just go around. Same as if the approach wasn't stable, go around. So in the cockpit of FedEx Flight 80, there was no sign of apprehension as this flight went on the way. Their 3-engine workhorse was doing exactly what it had done for years, safely hauling freight on the overnight trunk routes that kept FedEx global network running. But the 2 pilots were, however, probably looking forward to getting some rest in Japan, because, as is the case with most air cargo operations, they had started this flight in the middle of the night, leaving China just before 2 o'clock in the morning after only having a few hours of rest from their previous flight. On paper, this was a very straightforward leg, including a normal departure and climb out from Guangzhou, followed by a 3.5-hour cruise north over the South China Sea, eventually crossing into Japanese airspace for an approach and landing just before dawn. The radios crackled only occasionally with air traffic control handoffs, and the weather en route was calm, but while the plane itself didn't care about this early departure, the pilots controlling it likely did. On the cockpit voice recorder about 45 minutes before landing, the first officer brought up the subject that every pilot of an overnight cargo run knows all too well. He remarked to the captain that they were both tired, and the captain agreed. The first officer then added something along the lines of, "If it gets too quiet, make some noise." An offhanded comment showing their simple strategy here. Keep each other engaged so that neither of them would drift into any fatigue-induced lapses, which is how we pilots usually deal with drowsiness. As we have discussed before here on the channel when I covered the fatal accident of UPS flight 1354, fatigue can be the dark side of cargo operations. You see, unlike passenger airlines who tend to schedule their flights during daylight hours, since obviously that's when humans prefer to travel, cargo carriers instead operate on the backside of the clock. Packages need to connect through hub and spoke systems overnight so that they can be sorted, processed and eventually delivered during the following workday. And as a result, cargo aircraft tend to leave in the small hours, transit through dawn and arrive just as most people are getting up for work or even earlier. For the crews, this means duty periods that deliberately cut across circadian lows, so even when the formal rest requirements are met, the body's internal clock can still be a little bit out of sync. Physiologically, fatigue can look a lot like hypoxia, where pilots might not realize just how impaired they are until it's too late. Reaction times begin to slow, scan patterns become less thorough, callouts get sloppy, and you might start missing small cues, like a slightly high sync rate or a drift off the scent line. Stuff that would normally jump out at you. Now, some of you might interject here and point out that these 2 pilots were based in Anchorage, so what was night in Asia would be daytime at their home base. But these 2 pilots had also been flying daytime duties during their stint in Asia, which would have further complicated their circadian rhythm. Now, I'll get back to that issue soon, but I want to mention something else that affects everyone who is traveling internationally, and that's access to data connectivity. When I started flying, I used an old Ericsson phone, and to connect that for data in other countries on roaming would have cost an absolute fortune. So that meant that I had to buy local SIM cards and fiddle with swapping them around all the time, which was a nightmare. But thankfully, that's now all in my wake, thanks to today's sponsor, Holafly. Holafly are the leading global eSIM provider, keeping you connected in over 200 destinations, and without you having to swap any SIM cards or worry about roaming charges. Whether you are just leaving for a week or are constantly traveling the world, Holafly offers flexible data options to suit your specific needs. Once you have installed the eSIM, it connects instantly, which means that you can have it ready before you even land, and you can still use your original phone number for calling whilst using Holafly for the data. All of this, including the fact that you can cancel your plan at any time, makes Holafly perfect for pilots, cabin crew, digital nomads, or really anyone who lives a fast international lifestyle spanning the globe. Right now, Holafly is offering you, my viewers, 5% off their general eSIMs and a full 10% off their monthly subscription if you use the code Mentour. Just scan this QR code or use the link in the description below. I highly recommend them for your next trip. Thank you, Holafly. Now back to the video. For the first couple of hours of cruise in this flight, it was all perfectly manageable. The autopilot was engaged, the systems were humming, and there were a few check-ins with controllers as the flight crossed into Japanese airspace. But as the sun began to rise, the fatigue would have likely hit harder, since early morning is one of the body's natural low points. Now, with all of this said, none of this was unusual. It was just the life of a cargo pilot. Both of these pilots would have been well used to this. They were not unusually sleep deprived, and the report showed that they had both received adequate sleep and rest in the days leading up to the flight. But I still want to point it out, because as Narita loomed ahead of them, they were heading into the most complicated part of the flight, at the very moment when their mental sharpness would be most likely to be compromised. But whether this had much of an effect on what was about to happen, we will sadly never really know. Anyway, as FedEx Flight 80 descended in towards Narita's busy morning airspace, everything, like I said, looked completely routine. The checklists were completed as normal, the coming approach was briefed, and the radios were buzzing in the background with the calls from loads of other arrivals. So these two pilots were now busy doing what they had done countless times before, setting up their navigational aids, calculating landing distances, and programming their flight management computers to land their heavy aircraft safely after a long night flight. As this was going on up in the air, Narita Airport was just starting to come alive. The runways were already busy with morning arrivals, and controllers in the tower were juggling a mix of passenger flights and freighters streaming in from across Asia. But there was one factor that made this morning a little bit extra tricky, and that was the wind. It was not only strong, coming out of the northwest at around 30 knots, it was also gusty, with variations in wind speeds of up to 20 knots. Now, gusty winds create a number of different complications for us pilots. If the wind is coming at us from the side, known as a crosswind, the changes in wind speed will make it harder for us to keep the aircraft tracking down the centerline, as we constantly need to adjust our crab angle in response to these changing winds. Picture trying to drive a boat towards a specific point on a riverbank if the water speed around the boat keeps changing. And if the wind is not coming from the side but instead from the front, the changing wind speeds will come with a different problem. You see, the aircraft flies in relation to the surrounding air primarily. That's why we display our airspeed on our primary flight displays, and in still air we can change that speed with the help of our engines or with the help of our pitch. But if the wind is changing rapidly, that means that our indicated airspeed will as well, and we might have to start chasing it with the help of rapidly changing engine inputs. In the real world though, it's rarely either or when it comes to these issues, as we almost always get both crosswinds and headwind changes at the same time. So flying an approach with strong and gusty winds is always a challenge, but that's also what makes it so fun. Now, like I mentioned in the beginning, these winds were forecasted and would therefore not have come as a surprise for this crew. They also received at least one ATIS report as they were preparing for the approach, which was then followed by several updates from air traffic control as they kept getting closer. So the initial part of the final descent seemed to also have been completely normal, and the aircraft soon found itself approaching the ILS whilst initiating its configuration, and with the two pilots finishing up the approach and landing checklists. At time 0643, which was about 5 minutes before FedEx Flight 80 was due to land, Narita Tower passed along a pilot report from another airplane which had just landed on runway 34 left, the same runway that these two pilots were now approaching. That crew had encountered plus or minus 15 knots of wind shear on final below 2,000 feet. So aboard this flight deck, that would have meant that the airspeed seen by the pilots would have likely been quite erratic. One moment adding 10 or 15 knots, the next moment taking it away. Now these conditions are not by themselves dangerous if they're handled well. Plenty of flights every day land in similar weather conditions, and there's a difference between changing gusty winds and actual wind shear, which is normally defined as a sudden drop of 15 knots of airspeed or more, a sudden displacement of more than one dot on the ILS glide slope, a wind shear warning, or extreme thrust lever positions held for prolonged periods of time. If a full wind shear is identified, then a wind shear escape maneuver should be executed. But even before those criteria are met, it can be quite hairy to fly in these winds, as I explained before. Anyway, 2 minutes later, at time 0645, the controller then updated the pilots again. This time the wind came from 320 degrees with a speed of 26 knots, gusting 38 and dropping as low as 16. That's a spread of more than 20 knots between the peak of the gust and the lulls. And it should be mentioned here that with these type of strong winds, the air will move over buildings, trees and hills below and form vortices, which often leads to increasing turbulence as the aircraft descends. So the descent down the glide slope would have been quite eventful in this case. At time 0646, Narita Tower finally cleared Flight 80 to land. Winds at this time was called at 320 degrees at 29 knots, gusting 36 with minimums of 17. The tower controller's cadence when delivering these messages was steady and professional, but with a clear message. This wind was not calming down. Inside the cockpit, the captain now reconfirmed the runway. Runway 34 left, clear to land, followed by a word with high significance here. Stabilized. And after that, he just laughed a bit. That tiny laugh, caught forever on the cockpit voice recorder, is one of those small human details that stays with investigators and anyone really who studies this flight. I really want to point out here that something like that wasn't a sign of carelessness or dismissal. We pilots often use humor in moments of tension. It's a way of acknowledging the challenge without making it overwhelming. The cockpit is, after all, a workplace, and like most other workplaces, some dark humor can sometimes arise in very serious situations. So this did not in any way mean that the pilots were being unprofessional here. Now at this time, the airspeed was swinging beyond the plus or minus 10 knot window, typically used for determining if an approach really is stabilized. The gust spread was wide. Wind shear reports from other aircraft were fresh, none of it catastrophic on its own, but together they created a scenario where even a small misjudgment could quickly snowball. The captain had called stabilized as they passed the landing gate when that decision had to be made, and with those speed variations that they saw, they could have gone around there. And if they had done that, there's a possibility that none of what was about to happen would have occurred. But that call didn't come, likely because both of these men believed that they could land, as plenty of planes before them had already done that morning. And here I want to take a moment and say something about hindsight. You see, from the safety of our chairs and sofas when watching something like this, it's easy to say, well, why didn't he just call for a go-around? It's one of the first conclusions people reach when they look at approaches like this, but from inside of the cockpit it's not nearly that clear-cut. Airlines teach stabilized approach criteria as binary. Either you're stable or you're not. And if you're not within the criteria for altitude, speed, sink rate and configuration, you go around. End of story. But in practice, implementing that standard in very gusty winds is far from binary. Every gust moves the numbers. Airspeed needles swing up and down, sink rate fluctuates, and if we were to execute a go-around every single time a gust pushes us a few knots outside of the stabilized window, we'd likely never land during some of these type of weather conditions. And wind is often widespread over large geographical areas, so diverting to an alternate might not make things any better. So in those kind of conditions, the only workable approach is to sometimes judge the average and look at the overall picture. We will work together as a crew to assess whether over time the aircraft is on speed, on slope and under positive control, and that type of judgment requires experience and a willingness to accept small excursions, trusting that the averages will still meet the standard. So if the pilots would have rejected this approach, they could hold because they certainly had plenty of fuel to do so, but there was no guarantees that the conditions would improve for them. Yes, the winds were high, but not beyond published limits. Yes, the gusts were uncomfortable, but not outside of the operating envelope, and the aircraft remained on glide slope and relatively stabilized, so this crew just elected to continue, and it's kind of hard to blame them. But one thing that could have been considered here was for the more experienced captain to take over the controls and fly this approach. Today we have concepts like monitored approaches, where the first officer can still fly the approach and the captain then takes over for the landing under certain conditions. But that was likely not something that FedEx had considered at the time. Now, why the captain didn't consider flying the whole approach himself will never be fully known, but he must have just assessed that his first officer was more than capable of handling it. By time 06:48 and 3 seconds. That was just seconds before touchdown. The tower controller then made one last call. Winds 320 degrees at 27, gusting to 34, minimums at 18, meaning a slight crosswind, gusting nearly 20 knots above the lulls, right as the aircraft was passing overhead the threshold. Now, before we get to the landing, I want to take this time to discuss why landing this particular plane was so tricky. We have touched on it a little bit before, but to really understand what was about to happen, we need to step back from that windy morning in Tokyo and take a more hard look at the airplane itself. Because this accident wasn't just about tricky winds and possible fatigue. No, it was also about the MD11 and the compromises baked into its very design. You see, the MD11 was McDonnell Douglas's attempt to keep up in a world that was rapidly passing them by. By the late 1980s, wide-body air travel was being reshaped by a new generation of aircraft. The Boeing 767, the Airbus A310, and soon after that, the Airbus A330 and the Boeing 777. These were twin-engine, long-haul jets designed around the latest in aerodynamics and engine technology, able to cross oceans with lower fuel burn and less maintenance, which was clearly the future. McDonnell Douglas, on the other hand, had the DC-10, a product of the 1970s, which was reliable, powerful and widely used, but by the late 1980s it was definitely showing its age. Now, rather than starting fresh with a clean sheet twin like Boeing and Airbus had, the cash-strapped manufacturer instead tried to stretch and modernize what they already had, and eventually they released the MD11. Now, on paper, it looked competitive. A longer fuselage to carry more passengers, a redesigned wing with winglets for better efficiency, updated avionics to cut the cockpit crew down from 3 to 2, and Douglas had actually wanted to add an even more modern supercritical wing to the new aircraft, but had to settle with a beefed up wing with winglets due to budget constraints. The MD11 was also equipped with 3 big new engines, either Pratt & Whitney PW4000s or General Electric's CF6s, which gave it a lot of available thrust. And with this, McDonnell Douglas promised the airlines the best of both worlds. An aircraft similar to the familiar DC-10, which they already had supply chains and maintenance setups for, but with longer range, more efficient and a fully modern cockpit. But sadly, the airplane then turned out to not be able to live up to that sales pitch. Almost as soon as it entered service, Airlines found out that the MD11 couldn't really meet its promised range numbers. The jet simply burned more fuel than expected, and it even lagged behind its quad-engine rivals like the Boeing 747-400 and the Airbus A340. So some long-haul missions it was supposed to be able to do, like Europe to Asia non-stop, just wasn't achievable without payload restrictions, so the orders soon started to dry up. And to make matters even worse, new ETOPS regulations were then also released in 1985, which meant that for the first time ever, twin jets could now cross huge oceans along the same flight path as 3 and 4 engines jets had done before, rapidly shrinking the demand for the MD11 even further. But the real issue for the MD11's pilots wasn't the range or its economics, it was handling. McDonnell Douglas had cut down the size of the horizontal stabilizer at the tail to reduce drag and squeeze a little bit more of efficiency out of it. And also, as I mentioned earlier, the weight distribution had changed slightly, making the aircraft pitch controls a bit more sluggish at certain speeds and configurations. The engineers had done their math though, and they believed that the smaller tailplane and more powerful engines would still work because the MD11's updated flight control systems would help to compensate for it. You see, the MD11 came equipped with a suite of computerized augmentation systems designed to smooth out what the aerodynamics alone couldn't fix. One of the most important of these systems was the Longitudinal Stability Augmentation System, or LSAS, which was intended to provide pitch attitude hold, outer trim and increased pitch damping. And this system continuously monitored the aircraft's attitude through the flight control computers. If, for example, the MD11 would start to drift more than a couple of degrees away from its trimmed pitch, LSAS would automatically feed in elevator inputs to hold the nose where it was. And if turbulence bumped the nose up or down, well then LSAS would resist that motion and try to return the airplane to its previous attitude. So in theory, this system could give the airplane the stability of a bigger tail without the drag penalty. The airplane also had a fuel-based trim system, and LSAS could automatically command the fuel to be transferred in or out of a trim tank in the tail, effectively shifting the aircraft's center of gravity to relieve elevator loads. But that was mainly a cruise feature, and during the descent all fuel was transferred back from that tank in towards the middle tanks, making the aircraft more stable again. Now, alongside this LSAS system, the MD11 also had advanced auto-throttle logics, tied into a flight management system that was claimed by McDonnell Douglas to be state-of-the-art for its day. On paper, all of this was meant to reduce workload and to make the aircraft fly like a twin, in spite of its 3-engine layout and unusual balance. But the reality was that the automation had some limits. LSAS could keep the pitch steady under normal conditions, but it wasn't really designed to rescue the airplane during sharp maneuvers. It actually only had a 30% gain below 15,000 feet and could be overpowered by just 2 pounds of force on the control column. So, in a scenario where, for example, the pilots were pushing forward while LSAS was trying to dampen movement, the pilot inputs would not be counteracted, leaving the airplane to do exactly what the pilots commanded. So that's why a plane that looked fine on paper could become something slightly different when it was being hand-flown close to the ground. All of the features who had been added to increase stability at high altitudes were then less effective, and the dynamic issues affecting most large aircraft would still be very much there, leading to longer response times during large pitch inputs, especially at lower speeds. And if that happened, those slightly delayed responses could then be interpreted by the pilot as the aircraft needing more input, which could lead to a much bigger input before the response actually came. This led to a jet that was notoriously difficult to land well in tricky conditions. It demanded precision all the way down through the flare and touchdown, and small errors could become big ones very quickly. Also, where a Boeing 767 or an Airbus A330 of similar weight might cross the threshold at 135 to 145 knots, an MD11 often needed 155 to 165 knots to do the same thing. And with gusty winds, the wind additive needed could then run the speeds even higher than that, meaning a longer runway needed for landing. Now, the aircraft needed those higher speeds for its maneuverability, and if those speeds would bleed off early for whatever reason, the sluggish effect in pitch control could become even more pronounced. A side note here was also that the outer throttle was used throughout the landing in most airlines on the MD11. And it had been programmed to fit the touchdown requirements for an autoland, meaning a landing using both the autopilot and the outer throttle. To do this, testing had concluded that the outer throttle should start reducing the thrust back towards idle for the landing as early as 50 feet above the runway. But that would also lead to a large speed reduction during the actual flare, which would happen a little bit later. And if the landing was flown then without the autopilot engaged, the outer throttle would still start reducing the thrust back to idle at 50 feet, leading to lower speeds that would again complicate things for the pilot. Actually, the only airline who never suffered any serious landing mishaps with the MD11 was American Airlines, and it is entirely possible that their procedure of always disconnecting the outer throttle and land fully manually was the reason behind this. In any case, the pilots described that the effect of all of this was flying an airplane that always seemed to be a little bit ahead of you. On approach, it carried more momentum than crews were used to, which gave them perceived lesser pitch authority to finesse it down. If the pilot flared too late or too early and tried to reverse it, it could feel like the aircraft wasn't responding enough, leading to large overcorrections, and when things went wrong, well then they tended to go wrong in the same way, with a bounce. So the MD11 quickly earned a reputation for violent bounce landings. If the airplane hit hard and then rebounded, the pilots could quickly fall behind the aircraft and make pitch inputs that would just make the situation worse. And several MD11s have been destroyed in exactly this manner. A China Airlines Cargo MD11 at Hong Kong back in 1999 had broken apart after it had come down hard, bounced and then flipped upside down. And the same for a Lufthansa Cargo MD11 in Riyadh in 2010. Each time the pattern had repeated. A firm touchdown, a bounce, a nose-down input, and then structural overloads as the aircraft slammed back into the runway with way more force than the surprisingly robust landing gear structure could handle. All in all, the MD11 have suffered more than a dozen major accidents and incidents, many of them during landing, so by the mid-2000s it had one of the worst hull loss rates of any modern jetliner. Now again, FedEx knew this history. In fact, they had already lost an MD11 to a botched landing, FedEx Flight 14, back on July the 31st, 1997, which happened during a landing at Newark Airport in New Jersey, United States. On that approach, the jet had touched down long, and the captain, worried about running out of runway, had tried to get the airplane down onto the ground with far too much energy still on board. The aircraft bounced only 5 feet or so, but the nose gear was then pushed down because the crew, who was sitting far ahead of the aircraft's center of gravity, thought that the main gear was actually on the runway. This had led the captain to pushing forward on his yoke to get the nose down, and that forward push allowed the main gear to slam into the runway with 318% more force than the limit design load, causing it to collapse, the aircraft to flip over and immediately catch fire. Now, luckily both pilots had survived that accident, but the airplane was completely destroyed. The pilots on board FedEx Flight 80 obviously also knew about this accident, and so did, like we mentioned before, FedEx training department. Both of these pilots had therefore received bounce recovery training in the simulator, and they knew the rules. Keep the pitch angle at 7.5 degrees, add power, and if things got unstable, go around. But critically, this training was performed only once and was not given as part of their recurrent training. The training was also focused more on preventing tail strikes than anything else, as the ground spoilers on the MD11 could cause a pitch-up momentum during a bounce, something that ELSAS was later augmented to help with a system known as the PAP, or Pitch Attitude Protection. Anyway, back to the flight. With the wind still swirling across Narita, FedEx Flight 80 now continued into the last moments of its approach to runway 34 left. From the tower's vantage point, the MD11 looked stable enough, but to the pilots in the cockpit it was likely still a handful. As they passed 200 feet, the airplane was still moving at about 178 knots, which was way faster than the briefed VREF of 164 knots. But by 100 feet, the winds quickly shifted, meaning that the speed now reduced down to 154 knots, well below the minimum. And as that happened, the auto throttle didn't have time to react to it before going into its pre-programmed retard mode at 50 feet. Now remember what I said about the MD11's characteristics if the speed became too low? Yeah, this is where its mean character could really show itself. Unlike a 767 or an Airbus A330, which tend to forgive small errors in the flare, the MD11 demanded precision. And on top of that, the cockpit, which sat far ahead of the main gear, made it harder for the first officer to judge his height visually, something that would soon become an even bigger problem. Now the captain, acting as pilot monitoring, made no intervention at this point as the speed was decreasing. He had already called the airplane stabilized a minute earlier, and now both of the pilots seemed committed to bringing this aircraft down to the runway. The radar altimeter callouts now started rolling down in quick succession. 100, 50, 40, 30. And at 30 feet, the flare should have started with a smooth pull on the yoke to arrest the descent rate, but the first officer now was a little bit late, maybe focused on keeping the picture right and managing the swing of the airspeed needle. He waited until 20 feet to start his flare, and when he did, he likely realized that he was a little bit late and pulled a bit more than normal. But the aircraft, due to its inertia, didn't respond immediately. So he pulled more, leading to the nose suddenly moving up more than he wanted, causing him to reverse his inputs and push his yoke forward. And these slightly out of sync pitch inputs were what really started the whole accident sequence. The aircraft now responded to the pitch down command, increasing the vertical speed just as they passed over the runway. And that meant that the radar altitude callouts now all came rapidly with less than a second apart. A classic foreboding of an impending hard landing. With no added thrust to cushion the sink rate, the airplane now quickly moved downwards, and the airplane soon struck the runway hard on all three sets of its main landing gear. The flight data recorder measured 1.63 Gs of force as 430,000 pounds of jet, cargo and fuel met the concrete. As we mentioned earlier, the nose sits so far forward of the center of gravity on the MD11 that when the main wheels hit the ground, the cockpit could often feel strangely disconnected. Many MD11 pilots have described not realizing that they bounced until it was too late, so the airplane could feel like it had settled down on the runway when in reality the main gear had already bounced back up into the air again. And that is almost certainly what happened here. After the first touchdown, the airplane bounced back up in the air slightly, but the first officer may have believed that they were just rolling out normally, so he was now waiting for the nose wheel to start to come down. And it was at this moment, right after the first bounce, that the first officer's reaction to the situation created the next critical step in the failure chain. You see, his control inputs show that instead of holding the nose steady at 7.5 degrees or disconnecting the outer throttle to add thrust in order to cushion the bounce, he now instead again pushed forward on the yoke. The only logical explanation for doing that would be that he really thought that the aircraft was on the ground, so he wanted to get the nose to start de-rotating. Now, when it didn't respond, again due to inertia and because the aircraft's bounce trajectory, he added even more forward pitch, which with a delay soon turned the nose of the aircraft down towards the concrete below. So at time 06:48 and 22 seconds, the MD11 struck the runway a second time, even harder than before and with the fragile nose gear now impacting first, leaving some debris behind. The main gears came after, this time impacting with a force 2.2 times their design limit, bottoming out the struts and transferring the huge load directly into the fuselage. This impact reverberated throughout the fuselage at a low chest-thumping frequency. Investigators later estimated the vibration at around 3 Hz, with the entire airplane flexing and resonating like a struck drum. But up in the cockpit, almost 100 feet ahead of the main gear, the sensation probably wasn't quite as clear. The ground spoilers, which had started to deploy automatically after the first touchdown, now snapped closed again as the airplane lifted back into the air. And the reversers that had just begun to spool up were cancelled too, as the weight on wheel sensors suddenly detected no load on the struts. Now the touchdown of the nose and the impact of the main gear launched the airplane back up much higher than on the first bounce, about 16 feet off the runway. And for a brief moment, this situation could still have been saved if either of the pilots had recognized the danger, added power and held the nose up, or even executed a go-around. That would have caused the MD11 to halt the porpoising motion. It might still have touched down as part of the go-around, but eventually it would have started to climb away. Damaged perhaps, but largely intact. But again, no power came, and no call for a go-around or my controls from the captain. Instead, the nose started to soon drop again. The MD11 had pitched up briefly to around 7 degrees before it started moving nose down again, and at that altitude, especially in relation to the wide 60-meter runway, the bounce likely again felt smaller than it actually was in the cockpit, and the first officer's inputs were therefore again not in sync with the aircraft. So at time 06:48 and 27 seconds, the third impact came, which was the hardest of them all. The G-meter spiked past 3 Gs, and since the wings were now unloaded due to the first officer's forward pitch, the ensuing force on the landing gear went well beyond its structural limits. This was the breaking point. On that third slam into the concrete, the left main landing gear suddenly failed, but it didn't fail cleanly. McDonnell Douglas had designed it to shear away if it was struck by something horizontally while rolling down the runway, but vertically it had no such safe failure modes. By the time of this accident, planes were being built, requiring to have gear that could fail safely in both axes, but the MD11's construction predated those rules, so it had no vertical shear design. This meant that instead of detaching, the gear now translated all of that enormous force directly into the wing spar, which is a main component of the wing structure. That spar promptly failed due to structural overload, causing the left wing to bend and rupture the wing tank. Nearly 50,000 pounds of jet fuel immediately spilled out into the sparks flying from the now scraping metal on the left side, and that caused a raging fire, which quickly spread along the wing and behind the careening aircraft. With the left wing compromised, the right wing still generating lift and the left gear dragging underneath, the MD11 now quickly started yawing to the left, whilst also violently rolling over its detached left wing. This meant that in just a few seconds, the airplane was almost fully inverted, and at time 06:48 and 28 seconds, the cockpit voice recorder captured the chaos. A deafening bang, the master warning blaring, and the captain's final words, "Fire! Oh shit!" The ground proximity warning system provided a final bank angle warning before the recording abruptly ended. By time 06:48 and 29 seconds, the aircraft was then fully upside down, sliding along the runway already engulfed in flames. The inverted fuselage skidded until friction and structural collapse brought it to a halt beside the runway, and the fire then spread rapidly, fueled by a torrent of jet fuel spilling out from every ruptured tank. From the tower, the controllers had witnessed this horrific scene, and they actually activated the airport fire services even before the airplane had come to a complete stop. The fire trucks were rolling within seconds, but the blaze was so intense that there was no way for them to reach the cockpit in time. By the time the firefighters finally got close, nearly 40 minutes later, both of the pilots were sadly gone. Now, it is important to remember here that this whole sequence that I've just told you took less than 10 seconds. That's from the time that the aircraft crossed the runway threshold until it was upside down on fire in the grass. And that's actually less time than it took me to say that last sentence. After this accident and others with similar signatures, the operators of the MD11 adjusted. More emphasis was put on high sink rate prevention, clearer go-around triggers in gusty conditions, and recurrent practice for the exact scenario that had led to the accident of FedEx Flight 80. Now, I often talk about mental models for decision making and problem solving, like PIOSI, for example, but those models can only be used when there is time to evaluate the situation, gather information, and then discuss options with your team. This crash did not lend itself to any of that. In a situation like the one that these pilots found themselves in, the only thing that they had to rely on was their judgment, training, and experience, which sadly fell short. And that is part of what makes this accident so frustrating and also so understandable. Now, I have said it before and I'll say it again. Aviation is as safe as it is today because we add healthy margins to all potential risk factors. So, if there is one big lesson to take away from this, it is to always know when you start to eat into your margins and use that awareness to stop a failure chain from ever developing. The final report stated that the direct causes of the accident were the large nose-down elevator inputs made by the first officer before both the first and the second touchdown. This led to the first bounce and also the large force and nose gear touchdown in the second one, and his overall large pitch inputs without added thrust throughout this sequence eventually led to the outcome. But the report also cited the winds, the fluctuating airspeed, and the pilot monitoring's failure to intervene as contributing factors here. The design of the aircraft itself was not mentioned as a causal factor since its characteristics were known, and I want to send a special thanks to Captain Shem Malmquist here for contributing invaluable insights into the handling of the MD11. Without him, this accident would have been much harder to explain. Now, if you like this video, I would love for you to have a look through my backbook, where I think that you will find a lot of other interesting videos. There you will also see that the quality of the channel has changed a lot from the very first documentaries that we did to where we are today. And that's only possible due to the excellent team that I have behind me. Ari has helped me with the script writing for this episode, and either Dom or Mo have then made the editing that you're seeing with the help of our team of dedicated simulator pilots, Andrew, Nick and Samir, who do some truly fantastic work. Now, I'm telling you this because none of this would be possible without the fantastic financial support that we're receiving from our Patreons, who also get to watch these videos before anyone else and come with important feedback. If you also want to join this crew, well then click on this QR code or go to patreon.com/join/mentorpilot. I would love to see you in our next Zoom hangout. My name is Peter Hörnfeldt and you're watching Mentor Pilot. Have an absolutely fantastic day and I'll see you next time. Bye bye.